Hey, what's up, guys? Okay, so today I want to talk about this interesting combinatorics theorem, which is I recently find, and I think it's interesting. So I just want to share with you guys if you want to see more interesting topic or whatever mathematics you want to see, that you can subscribe to my channel. Don't forget to okay. Basically the settings list. So A will be, let's say, n by m, sorry, m by n matrices, and the B will be n by n matrices. So this left hand side determinant AB can be written as the determinant of A J1 up to Jn, B J1 up to Jn, where J1 from 1 to n. Okay, maybe a little bit hard to explain. So basically the idea is that you can take all the combination from 1 to m. So you just sort of n choose m. There are all the choice, and you can order then you can choose n from m, and you order m, and then collect everything, and then take A, which is matrices, and you take only J1 up to Jm, so become a sub matrix. So this will become a sub matrices, which is a square and m times m. And this B is also a sub matrices, square, the m and the m times m, and you collect them, and using the you can collect them and using these sub matrices to calculate determinant. Okay, and then all these are also this sum contains n choose n. Okay, and these J1 are J2, J1 up to Jm are just label. So for example, let me just write down, for example, your A is this, and for example, your J1 is 1, maybe J2 is 2, and J3 maybe is 5. So you get 1 and 2 and 5. So you get 1 and 2 and 5. And you all use all these guy, right? Collecting them as a 3 by 3 sub matrices. And then calculate determinant of it, and then take it, and then combine everything, and then become determinant AB. Okay, maybe hard to explain. So let me just provide an example. Okay, so that you guys know what hell is going on. For example, I can take A to be 1, 1, 2, 3, 1 minus 1, and the B to be 1, 1, 3, 1, 0, 2. Okay, so this is M is 2, N is 3. So first I calculate AB. Okay, and you can calculate by yourself. AB is 4662. So if I calculate determinant AB, then I will get 8 minus 36. So it's negative 24. Sorry, negative 28. Okay, so by this Cauchy Binet, then I should take, there are 3 choices, right? So because I need to choose 3 from 2, right? So there are 3 choices. Okay, and what kind of 3 choice? Basically, we will have three choice, 3 choose 2, right? 3 choices. So I can take J1 to be 1, or J2 to be 2, or J1 to be 1, J2 to be 3. Important is J1, J2. J2 need to be greater than J1, right? So J1 is 2, or J2 equals 3. And you calculate the sub matrices. So for example, you take A, J1, J2, where is A12. So A12 is this. 1, 2, 1, 2. Okay, so it's 1, 1, 3, 1. Okay, and you can calculate, let's say, you can also calculate B12, right? So B12 is here. So 1, 1, 3, 1. And then you can calculate the A13. Okay, so A13 is 1. So, okay, so you can see now it's A13, right? So, maybe a little bit hard to see. Right, but 13 is just 1 and 3, right? So just you take 2 of it, right? So you take 1, 3. So you take this one and this one. Okay, so you can imagine that this is 1, this is 3. Okay, so it's 1, 3, 2 minus 1. Basically, since n is larger than m, right? So you should there, this is n, right? And you take m of it, right? So in general, m should be there, so you could n. Otherwise, there's otherwise you cannot do anything. So it's 1 and 3, right? So we take m. So it's the J1, J2 up to Jm. Okay, so it's this. So it's 1, 3, and 2 minus 1. Okay, how about B1, 3? Oh, so B1, 3 just do the opposites, right? So it's 1 and 3. So it's 1, 1, 0, 2. And then you can take A2, 3. So A2, 3 is 1, 2, 1 minus 1. And the B2, 3 is 3, 1, 0, 2. Okay, let's do some very interesting task. So let's calculate the determinant of is A12, determinant of B12 plus determinant of A13, and the determinant of B13, and the determinant of A23, and the determinant of B23. Okay, so let's quickly do it. Yeah, let me just write down a number so that okay, I cannot change the color. Fine. Is it? Okay, nice. Okay, I can change. Okay. So the determinant is -2. Okay. And this guy is also -2. And then this is -1 times -6, so it's -7. And this guy is what, 2, right? So 2. And then this guy is -1, -3. -1, yeah. And then this one is 6. Okay. So we get -2 times -2 plus -7 times 2 plus -6 -3 times 6. Okay, so 4 plus 4 minus 14 minus 18. Okay, so it's -28. Okay, so same as you just calculate determinant AB. Same as you just calculate determinant AB. Okay, so this is the idea, and yeah, this is the idea. So let's dive into the proof. Yeah, proof is a little bit tricky. So before we did it, we need to do something. Okay. So do some preliminary. Okay, so let me just write down. So our proof AB is the determinant of AJ1 up to JM, and hopefully you understand what's the meaning of it. So we will not suck, right, if we don't understand the meaning of it. Okay. And okay, so before we do this, let me first recall the definition of determinant, right? So the determinant of A will be what? Will be just, you can calculate as I, right? So you can calculate like A, yeah, so 1. Okay, so let me just write this using this notation. So determinant of A will be what? Will be just there's a -1 to sign, right? Sorry. So let me just write some tensor, which epsilon, which is let's call it I1, I2, up to maybe IN. Let's say this is n by n. And then we take the product of AIs and okay, so let me just use this. So I take the matrices and I take one, I take the, but basically it's a product of, let's say this is K, you may be using, okay, so let's maybe use this. So it's hard usually it's hard, I mean, to be hard. Let's write it as I sigma I, right? So I from 1 to n, and for each sigma, which is a permutation, and you take the sign, which is epsilon of sigma 1, sigma 2, sigma n. And there's sum over all the permutation. Okay, so this is the determinant. Hopefully it's familiar to you. Okay, so let's check. Okay, so notice that let's say if I consider epsilon L1, L2 up to Lm, and obviously it's the same as this guy, right? It's the same as minus of epsilon K1, K2 up to Km. Except, so basically this term is the same except basically your L1 up to Ln need to be basically from 1 to n, and then this guy must be 1 to n, except like these, so these two are the same. so these two are the same if except these two are the same if K1 and Km are different parities. Okay, different parities. If they are the same parity, then it's 1. So basically, the proof idea is that for example, if you take the determinant of these, right? If you take a determinant of Bj1 up to Jm, okay, you can translate this into the any kind of permutation, right? So for example, you can take let's say epsilon K1, K2 up to Km. So basically, this guy is the another sign tensor here times this. You can this guy will become like the determinant that's will become determinant of B of K1 up to Km. So J1 or Jn are by definition need to be fixed order, and for these B K1 to Km cannot may not be a fixed order. Okay, so basically maybe K1 from Km is like 1, 3, 2, and the J1 from Jm must be 1, 2, 3. Okay, so for example, this is 1, 2, 3, and this guy can be 1, 3, 2, and then obviously their difference will be a tensor like 1, 3, 2. Okay, so hopefully it's easy. 1, 1, 2 is -1, right? Because so determinant will be just the permutation of this. Okay, so once we have this and with these two definitions, then we can start to write down our proof. Okay, so our determinant AB, by definition, we can take. Let's say we take L1. Okay, up to Lm. So notice there this is no any order, right? Because by definition, your determinant comes from any permutation. So permutation need not to be order. Okay. So you can take it from M, and you take epsilon L1, L2, as we just say. So given a permutation, you compute the sign. Now take AB, right? So it's product of, so it's A 1K, BK L1. Right? By definition, is these guys from 1, so 1 sigma 1. So you get 1 sigma 1, right? But in this case, you get A1 L1. Sorry, in this case, you get AB 1 L1 by definition, where is a summation of A1 K1 B K1 L1, and the K from 1 to N, right? By your definition. Okay, so you get so for this one that you get 1 K B K L1. Let's say right, it's K1 K1, and the K1 from N 1 to N. Okay, I will be a little bit sloppy, and then I guess another which is K2 from 1 to N, and the A 2 K2 B K2 L2. Okay, up to K Km, right? So Km equals to 1 in N, and the A M B K L M, right? So B K M and the MK. Okay, so this is just right by definition. Okay, so now you can expand it out. Okay, so you can expand it out and collect all the K. Okay, so you can take it to be 1 from 1 to K1 up to Km, that's equal to N, and you collect A, right? You collect A out, so you get A1 K1, A2 K2 up to AM Km, and then collect each L, right? So obviously this is the only thing you can do, right? Because the L indices only come from B. And the BK1 L1, BK2 L2 up to BKM LM. Okay, so yeah, this is indices. Okay. Okay, so what is this? By your hands, by your looking, right? This is L1 from LM, and this is K1, K2, Km, right? So if you view K1, K2, Km as a submatrices, then you are basically permuting all this, right? So you get determinant of B, K1, K2 up to Km. Okay, so now you get this and this. Okay, so now you can extract this determinant B using our previous formula, right? Determinant B, although it's not obviously order, but I can fix it order, right? I can fix the order and then into the J1 up to Jm, which is a fixed order permutation. Okay, so I can write it as summation I from 1 from K1 up to Km less than M, and A1 K1 A2 K2 up to AM KM. And I write this guy as a epsilon tensor, right? So that epsilon of K1, K2 up to Km, and the determinant of the J1 up to Jm. So now these guys already fixed, right? Already fixed. Okay, so what's the final results? Okay, so look at this. What is this? Okay, so so now each K1 up to Km are already fixed to be J1 up to Jm, right? So what is this? Or I should say what is what's the so what is this? If I collect determinant of this and then change it into the fixed form, so for this each term, right, I will create a epsilon K1 up to Km term, which come from here. Okay. And your determinant K1 from K1 up to K up to M will take a epsilon K1 K2 up to Km, right, and then sum over it. But notice that these K1 and K2 can be what? Can actually be repeated, right? Because this K1 or K2 are actually can be repeated. Okay, so this tell you what? Okay, so this tell you that this tell you that what? This tell you that these terms, if you fix this term, right? If you fix that, for example, let's say B is 1, 2, 3, and then this will be this K1 will be like 1, 3, 2 or something. We'll generate this. Okay, so these terms actually for each K1 and up to Km less than M, do not repeat it, will generate determinant A, right? So we'll give you determinant A. Right, but as J1 up to Jm already forced that this K1 up to Km must be the permutation of J1 to up to Jm. So this will force the previous one A to be determinant of J1, J2 up to Jm. Because this tensor must be the permutation of these tensors. Okay, so this permutation will force these guys, right? For example, this is 1, 2, 3, right? This guy must be 1, 2, 3, and the 2, 3, 1 something. And then this will give you this. Okay. Okay, so then you will force K1 up to Km to be J1 up to Jm. Okay, so you can just replace this and become this. It will become J1 J1 let's say J1 less or equal to J1 less than J2 less than J3 and up to Jm equals to A. Sorry, not need to be less or equal to less equal to yeah. Okay, and this guy will just be determinant of it. Okay, and yeah, so this is the proof. Okay, so basically, one might worry that maybe in this place that there is maybe some of you may worry about this A of A1 K1 A2 K2 AM KM times this should not just be a determinant of this, right? But this is not true, right? Because you need to consider that in this case, right, you are already do the pre-order, right? So this L1 up to Ln less than or equal to n actually become will actually create any kind of somehow like pre-order from J1 up to Jm and fixed on this determinant B. So whenever you sum this, there will always a determinant B where already come from here once you fix this K. Okay, so this is why there's another summation. You need to account for J1 up to J2 up to Jm less than A. Okay, so this is a proof, and yeah, so there's some consequence that yeah. Okay, by the way, so this consequence can actually give you the quickly proof of this. Okay, if all these are n by n matrices, right? Because if n are n by n matrices, there's no freedom that you can choose indices. Okay, so this is the simple Cauchy Here's a simple example. Okay, and another example is that if you take A to be the n by n matrices, and you just want to calculate determinant of A and AT. Okay, so you can take out you can take one from J1, J2 up to Jm, that's equal to m, and the determinant of AJ1, AJ2 up to Jm, then the squared. Okay, so by the way, so somehow like I forgot to say this. Originally, the original definition of this this A should take the columns. Sorry about this. I forgot to say that this is to take rows. Okay, so take all the columns of A, and B is take all the rows of A. Then you can get the correct sum of matrices, right? I mean, this is intuitive because this is the only thing you can take. Okay, so yeah, see you guys next videos. Yeah, this is all I have to say.